Good evening, students. Today I am going to discuss the concept of electric field lines. As you know, in the last class we discussed the electric field and the electric field intensity. Electric field is a space around a charge or a group of charge, and electric field intensity is a mathematical quantity used to measure the strength of electric field. Now today's concept, electric field lines. This concept was developed by Michael Faraday. The purpose of this electric field line is to express the electric field region pictorially. That means in the electric field region we have a mathematical quantity electric field intensity. The same electric field region can be pictoriously expressed with the help of electric field line. Now what is this electric field line? What is its definition? Electric field line is an imaginary path, maybe straight or curved path in the electric field along which a unit positive charge will move if it is allowed to move freely in the electric field. That means electric field lines are imaginary straight or curved path. They are not actually present around a charge. We imagine that there are paths in the electric field region. What is this path actually means? This is a path of positive charge where it is allowed to move freely in the electric field. Using these electric field lines, we can get the magnitude as well as direction of electric field intensity. So that is the use of electric field line. Using electric field lines, we can measure the magnitude of electric field intensity as well as direction of electric field intensity. Now, how you will get the magnitude and the direction of electric field intensity using this electric field line, we will discuss it in the coming slide. The direction of electric field intensity at any point can be obtained by drawing tangent to the electric field line at that point. So to get the direction of electric field intensity, what we have to do? You draw an electric field line, then at every point you can draw different tangents. Each tangent shows the direction of electric field intensity at that point. Now let us see some examples of electric field line drawn around different types of charge. Let us start with a single point charge. So this slide shows electric field line around a positive Q charge as well as around a negative Q charge. On the left side you can see a negative Q charge, and around that negative Q charge you can see electric field lines are straight. These are straight lines. So around a single minus Q charge, the nature of the electric field line is straight line. Direction of electric field line is towards. You see here the arrow marks are directed towards this minus Q charge. Whereas you look at the right side picture, that is electric field line due to a plus Q charge. Around plus Q charge, the direction of electric field line is again straight. Line is straight in nature, but the direction is away. So you see only one difference in these two pictures. In minus Q charge, the direction of electric field line is towards. In plus Q charge, the direction of electric field line is away. I have doubt regarding this direction. Why it becomes towards? Why in the case of plus Q charge, the direction of electric field lines become away? Get the answer. You just remember the definition of electric field line. It is the direction in which plus 1 coulomb charge moves. So you imagine plus 1 coulomb kept here. Due to the attraction, this plus 1 coulomb will move towards minus q. When you keep plus 1 here, minus q will attract plus 1 towards it. That's why the arrow mark is towards minus q. Look at the other picture. Why the direction of electric line due to plus q charge is taken away? The reason very simple. If you keep plus 1 coulomb charge, whether here force of attraction or repulsion, positive 1, positive q. So due to the repulsion, plus 1 kept here will move away. That's why the arrow mark is put away. Clear? So, the conclusion of this slide is a single point charge produces electric field straight line in nature, and the direction depends upon the nature of the charge. Plus q, the direction will be away, minus q, the direction will be towards. The next slide shows nature of electric field lines around two charges. Left side you can see two charges, plus q and minus q, unlike charges. Here you see plus q here, this red dot shows plus q, this red dot shows minus q. See these yellow curves, these yellow are curves, not straight lines. So in this figure, you see electric field lines are curved lines. That's why in the definition, electric field line may be straight or curved. Here this example shows curved nature of electric field line. Here you see some other properties also. Let us check the direction of electric field line. It's away from positive charge and towards the negative charge. So from this figure, we can conclude the electric field lines starts from positive charge, ends on a negative charge. Also from the figure, you can get the direction of electric field intensity. You see at P, there is an electric field line passing through that point P. If you need the direction of electric field at P, you simply draw a tangent to this curve. Which curve? Electric field line curve. This is the tangent represented by this line. This tangent gives the direction of vector E. This is the main use of electric field line. By drawing electric field line and creating tangent to that line, we will get the direction of electric field vector. Clear? Look at the other picture. This is also electric field line around two charge, but this time similar charge, plus q plus q. You see, electric field lines are curved again, directed away because positive charge electric field line is away. When you compare these two lines, another important property you can see here that is written on the bottom. Due to this force, which force plus q minus q, attraction, electric field lines contract lengthwise. Here you see the distance between electric field line become narrower and narrower when we approach towards the center. Here the distance between electric field line is larger. When we go towards the center, it reduces. This is the property of electric field lines due to two unlike charges, plus q and minus q charge. Electric field lines contract lengthwise due to the attraction. Now let us see here. Here is unlike is like charges, plus q plus q. So which sort of force? Repulsion or attraction? Repulsion. So due to the repulsion, you can see a lateral or sidewise pressure. Sidewise pressure. Due to the pressure, you see no electric field line is trying to move to this point. So here at the middle, you see electric field lines keep away from this midpoint. Electric field lines are eagerly entering into this middle region. There is a contraction of electric field lines. Here, electric fields keep away from this point. This is due to repulsive force. Coming to the fourth figure. This is the fourth figure. Right top you can see again green lines are drawn. These green lines again shows the direction of electric field line between two metal plates. These are metal plates. This is a metal plate with a positive charge. This is a metal plate with a negative charge. When two metal plates oppositely charged are kept with a certain separation, the nature of the electric field lines in between the plate will be straight, parallel, equidistant. You see three different properties here. Electric field lines are straight, electric field lines are parallel, and electric field lines are equidistantly separated. Equal distance of separation. This is a unique field. Peculiarity of electric field in this region is uniform. So wherever electric field is uniform, nature of electric field line is straight, parallel, equidistant. Clear? Means a uniform electric field region can be pictoriously represented by the straight, parallel, equidistant electric field line. Yeah. Coming to different properties of electric field lines. There are 8 different properties for electric field lines. Many of the properties are already seen in the earlier slide. I think the first property is familiar one. Electric field lines or electric lines of force, both are the same. Electric field line, another name is electric lines of force. They are imaginary lines. As you know, in the definition, we started off with the statement, electric field lines are imaginary, straight or curved path. So this is a familiar property. Second property, I think that one also familiar. That property says, a unit positive charge placed in the electric field tends to follow a path along the field line. Free to do so. What mentioned in that definition? Electric field lines are path along which positive charge will move if it is allowed to move freely. Now the third property also we discussed in the earlier slide. Electric field line starts from positive charge, ends on a negative charge. Instead of word starting, here same meaning. Ends. Instead of word ends, terminate. So we can replace it with the starts, terminate with the ends. So electric lines of force starts from a positive charge, ends on a negative charge. The fourth property. Tangent to an electric line at any point gives the direction of electric field at that point. You see an electric line, this yellow curve shows electric field line. P is a point on this electric field line. To get the direction of electric field intensity at P, simply draw a tangent. This is the dotted line shows tangent. So this tangent indicates direction of vector. Now coming to the fifth property, it's an important property. Two electric field lines or electric lines of force can never cross each other. Clear? That means no two electric field lines can intersect. രണ്ട് ഇലക്ട്രിക് ഫീൽഡ് ലൈൻസ് ഒരിക്കലും കൂട്ടിമുട്ടില്ല എന്നാ പറയുന്നത്. അപ്പൊ ചിലപ്പോൾ ചോദിക്കും എന്തുകൊണ്ട്, വൈ? I think last year question paper there is a question like this. No two electric field lines can intersect each other. Why? So how will you explain two lines will never intersect? So this is what explained in this figure. You see two curved lines, yellow curve and another yellow curve. These are electric field lines. They are intersecting. Actually, it is not possible. That's why അതിന്റെ മുകളിൽ ഇങ്ങനെ എഴുതിയിട്ടാണ് നോട്ട് പോസിബിൾ എന്ന് പറഞ്ഞാൽ ഇങ്ങനെ ഒരു സംഭവം ഇല്ല, കൂട്ടിമുട്ടില്ല. ആ മുട്ടാത്ത എന്തുകൊണ്ടാണെന്ന് എക്സ്പ്ലെയിൻ ചെയ്തത് മുട്ടിയാൽ എന്താ പ്രശ്നം കാണിച്ചുകൊണ്ടാണ്. രണ്ട് ലൈൻസ് ഒരിക്കലും കൂട്ടിമുട്ടില്ല. അപ്പൊ സാറ് പറയുന്നത് ഇവിടെ ഇലക്ട്രിക് ലൈൻസ് മുട്ടില്ല. ഇവിടെ പിക്ചറിൽ കാണിച്ചിട്ടുണ്ടോ ലൈൻസ് കൂട്ടിമുട്ടിയാൽ. ഇവിടെ ലൈൻസ് കൂട്ടിമുട്ടിയത് എന്തിനു വേണ്ടിയിട്ട് മുട്ടിയാൽ എന്താ പ്രശ്നം ഇന്റർസെക്ട് ചെയ്യാനുള്ള പ്രശ്നം എന്താണെന്ന് പറയാം. Suppose if two lines intersect at a point, at the point of intersection we can draw two tangents. You see, one tangent is this one, dot line. This tangent is drawn at this point considering this lines of force, this line of force, this one. Again at the same point another line is coming. Okay, this is the second curve. With respect to this curve at this point, sorry. With respect to this curve at this point we can draw tangent here, tangent. So at this point you can see there are two tangents, E1, E2, indicating two directions for electric field intensity. At a point there will not be two directions for electric field intensity. That's why such a situation will never arise. Situation intersection of electric field lines. Clear? I will explain once more. No two electric field lines can intersect each other. Why? Answer. If two electric field lines intersect at a point, at the point of intersection, we can draw two tangents indicating two directions for electric field intensity at that point, which is not possible. Clear? This is what you have to write. The reason behind non-intersection of two lines of force. Clear? Now coming to the sixth property. The number of electric field lines are closer. Closer means near to each other, crowded, where electric field is stronger. That means strength of electric field intensity can be obtained by looking the crowdness of electric field lines. If the lines are spread out means widely separated, that region is a weak electric field region. That means crowdness and spreading of electric field lines shows strength of electric field in that region. If the electric field is strong, electric lines of force are crowded. If the electric field strength is weak, electric field lines are spread out. Clear? Now the seventh property. Electric lines of force are perpendicular to the surface of positively or negatively charged body. Here you see a conductor which is given positive charge. You see electric field lines are perpendicular to the surface. Surface is normal charge. This picture will give you more idea about that statement. You see the surfaces are irregular in shape. Positive charges are given. See the direction of electric field is exactly perpendicular. Tangent വരച്ചിട്ടില്ല നമ്മൾ perpendicular ആയിരിക്കും. Tangent ഇങ്ങനെ വരിക. It's an important property. Electric field lines are perpendicular from a charged conductor. Ninth property. Electric lines of force contract lengthwise to represent attraction between two unlike charges. We discussed this in earlier slide when we consider the electric field lines around two unlike charges, plus q minus q chargeകളുടെ നേരത്തെ ഒരു പിക്ചറിൽ അതിലത്തെ കാണിച്ചിട്ടുണ്ട്. Also, electric lines of force exert lateral or sideways pressure to represent the repulsion between two like charges. Then also seen in the earlier slide, electric lines of force around two plus q charges. So these are the 9 different properties of electric field lines. So you have to take down all these properties of electric field lines, and also you have to take down one more question here. What is the question? No two electric field lines can intersect each other. Why? I discussed the answer. If two electric field lines intersect at a point, at the point of intersection we can draw two tangents indicating two directions for electric field intensity, which is impossible. So that's about electric lines of force. Coming to the next concept. That's about electric dipole. Now what is this electric dipole? Electric dipole is a system of two charges. System of two charges means a positive charge and a negative charge. Equal and opposite. Separated by a very small distance. So what is an electric dipole? Electric dipole is a system of two equal and opposite charge separated by a very small distance. Here you see one picture of electric dipole. You see a minus q charge and a plus q charge with some separation. Here the separation is represented by 12. Means if this is minus 5 coulomb, this should be plus 5. Then only this system is said to be dipole. ഏതെങ്കിലും രണ്ട് ചാർജ് വെച്ചാൽ ഡൈപോൾ ആവില്ല. രണ്ട് ഒരേ നമ്പർ ആയിരിക്കണം, ഓപ്പോസിറ്റ് സൈഡ് ആയിരിക്കണം. ഇത് the strength of an electric dipole is measured with a quantity called electric dipole moment. Dipole moment. What do you mean by dipole moment? Dipole moment is a vector quantity used to represent the strength of an electric dipole. Electric dipole എത്ര സ്ട്രോങ് ആണെന്ന് കാണിക്കുന്ന ക്വാണ്ടിറ്റിയുടെ പേരാണ് dipole moment. It's a vector quantity, so it should have magnitude as well as direction. To get the magnitude of electric dipole moment, it is measured as the product of magnitude of one of the charge and the distance between the charges. ഏതെങ്കിലും ഒരു ചാർജിന്റെ മാഗ്നിറ്റ്യൂഡ് എടുക്കുക. മാഗ്നിറ്റ്യൂഡ് മൈനസ് ക്യൂനും പ്ലസ് ക്യൂനും മാഗ്നിറ്റ്യൂഡ് ക്യൂ തന്നെയാണ്. ഭാഗം ക്യൂന് എന്ത് ചെയ്യണം? ഡിസ്റ്റൻസ് ബിറ്റ്വീൻ ദ ചാർജ് കൊണ്ട് മൾട്ടിപ്ലൈ ചെയ്യണം. ക്യൂ ഇൻറ്റു 12. ക്ലിയർ? Direction of this vector. The direction of dipole moment is taken conventionally from negative charge to positive charge. അപ്പോൾ ഇവിടെ ലെഫ്റ്റ് സൈഡിലാണ് മൈനസ് ക്യൂ ഉള്ളത്, റൈറ്റ് സൈഡിലാണ് പ്ലസ് ക്യൂ ഉള്ളത്. അപ്പോൾ എങ്ങോട്ടേക്കാണ് നെഗറ്റീവ് ചാർജ് ടു പോസിറ്റീവ് ചാർജ് ഡയറക്ഷൻ? റൈറ്റ് ഡയറക്ഷനിലാണ് ഇവിടുത്തെ ഡൈപോൾ മൊമെന്റ്. നമ്മൾ മൈനസ് ക്യൂവും ഇവിടെ നമ്മൾ പ്ലസ് ക്യൂ വെക്കുന്നെങ്കിൽ, അതായത് റൈറ്റിൽ നമ്മൾ മൈനസ് ക്യൂവും ലെഫ്റ്റിൽ പ്ലസ് ക്യൂ വെക്കുന്നെങ്കിൽ direction of dipole moment will be leftward. Electric dipole moment എന്നുള്ള ക്വാണ്ടിറ്റിയുടെ യൂണിറ്റ് കൂളം മീറ്റർ. That's represented with a capital C യും small m. It's not read as centimeter, it is coulometer. Centimeter ആണ് വായിക്കുന്നത്. ഇത് കൂളം മീറ്റർ എന്നാണ് വായിക്കുക. ക്യാപിറ്റൽ സി കണ്ടു കഴിഞ്ഞാൽ കൂളം എന്നാണ്. Charge in the unit coulomb, distance in the unit meter. Clear? So we discussed the electric dipole and a dipole moment. For today, this much is enough. In the next class, we have to discuss further about this dipole and its electric intensity. So in the next class, we will derive expression for electric field intensity due to an electric dipole. So till then, bye.